Hi, this is a follow-up video on my EcoFlow Delta Pro battery here, which I've been using for quite some time to power my one of my fridges, not this chest freezer next to it. It's actually powering the main fridge in our house, and I'll put up some details of that. It's a Westinghouse jobby, and it's the family fridge. It gets used all the time. I don't know, like it gets opened 100 times a day or something. But anyway, the interesting thing is that this is a 3600 watt hour or 3.6 kilowatt hour battery. Okay, it's quite sizable. It's one of the biggest ones you can get in like this portable form factor, and it's barely enough to actually power that one fridge for 24 hours. Now, it can actually do it. There's, but it doesn't have a huge amount of margin. And I've tried doing the main fridge plus this chest freezer here, and these chest freezers are very efficient. And there you go. You can get the rating of that, 225 kilowatt hours per year. But so they're very efficient, and the one inside the main fridge is not, because it's not a chest freezer and it just gets opened all the time every day by a family of 4. Anyway, I did actually try using this to power like this chest freezer as well as the main fridge, and it could barely do it. Like some days, yeah, it was going to cut out. It wouldn't have the juice. Anyway, I do actually have it hooked up to a timer up here, so it comes on at about 10 a.m. When the sun's out, and it charges up. It charges up at the fast rate, and I've got it set so it charges to 90%, and it's now almost 12 o'clock. And it charged up at, started charging at 10 o'clock, and it's reached that 90%. As you can see, it's drawing 86 watts, and it actually says, the battery management system says it can go for another 6 days at 86 watts. Well, this morning I came out and had a look, and it was down to 10%, and that was around 8 a.m. So, yeah, it goes from 90%, at now, which is 12 o'clock midday, and by 10 a.m. the next morning, it's down to 10%. So it's kind of like just makes it. Of course, it depends on how many times we open it and the ambient temperature, etc., right? But there's just something not right about this. Now, somebody on Twitter, thank you very much, who says that they do some sort of product support for EcoFlow. I'm not sure if they're officially an employee or not, but they said because this uses LPF battery technology, there is an issue with the battery management system and the display. And she said that it would take, it'd actually stay at 1% for quite a significant amount of time, i.e. it's not really a linear type thing. There's something, there's something wrong with it. So anyway, I thought I would whack a load on this thing, like a controlled and measured load, and actually measure the capacity of this battery based on its output capacity. Now, the 3.6 kilowatt hour rating of this thing, I'm absolutely sure, is the internal battery capacity, i.e. it contains 3.6 kilowatt hours of batteries, right? I have no doubt about that. But that rating is for the batteries. That doesn't include the efficiency of the inverter, because just having this mains inverter on is going to chew some residual charge, and just to keep it running even with no load, and which is what you expect, of course. Every inverter is going to do exactly the same. Like my small Yeti up here, for example, that'll do exactly the same thing. In fact, this has got a significant self discharge on it, just because that displays like it's actually, it's always kind of like running there. So, over a month or two, a couple of months, it does actually discharge a significant amount. But anyway, turning the inverter on does have quite, the power draw. So anyway, I don't believe the rating of 3.6 kilowatt hours is like output referred, as we'd call it in the industry, an output referred rating, i.e. you're not going to get 3.6 kilowatt hours on the mains output here, because that's the battery capacity. Then you've got to subtract, as I said, like the inverter, and the efficiency of that's going to change with the output power, of course, but we don't have any details about that. So anyway, I'm going to hook up a load, see if I can measure the capacity of this thing. So I'll charge it up to 100%. Then we'll start. So I've got the phone app here connected via the Wi-Fi. As you can see, it's 39 degrees internally, and 6 days and 12 hours left at the current consumption rate of 90 watts, which is what the fridge is taking at the moment. As you can see, it's fairly constant there, but, you know, it goes in and out as the compressor and other things turn off and on. I don't think it doesn't often get down to 0, so it seems to be like, you know, fairly consistent in terms of, anyway, it still says that it'll do at 90 watts, it'll do, you know, 6 days. So anyway, let's charge this sucker to 100%, shall we? So I'll go right up to 100%. There we go. And that should start fast charging this sucker now. And yeah, there she goes. All right. So she's going to fast charge. We'll go to 100%. And so I'll get the full capacity of the battery, and then I'll put a load on it and actually measure the energy draw output referred, so what the load actually draws. All right, we're almost there charging it up. Not sure it's actually going to get to 100. It seems to be stuck there, but anyway, here's a DaveCAD of what the sort of like efficiency curve is going to look like for a battery like this, and this will apply to EVs as well. This will apply to electric vehicles. You're talking about the percentage loss of the capacity of the battery versus the load. So, you know, if you're driving an EV, for example, there's going to be an optimum speed at which the efficiency is going to be the best. And the same thing here. So we've got percentage loss versus the load here for the battery. And when you've got no load, you're actually going to get basically like an infinite amount of loss, because like per load, because there's zero load and you've got to chew some of it to drive that inverter, of course. But, you know, as you increase your load, it doesn't necessarily have to look exactly like this. It's going to be flatter for a much greater period. It depends on, you know, the efficiency curve of the inverter circuit used inside this thing. But yeah, basically it's going to be a sweet spot. So anyway, I'm going to drive this. My load is going to be this Cambrook heater here, which you've seen in a previous video with those double adapters. I'm going to put it on the 1 kilowatt setting here. So it's going to be a 1 kilowatt resistive load here. Then I'm going to use my MetroHit energy meter, and I'm just going to log the output power so we can get the output referred energy. Will it be 3.6 kilowatts? No, I expect it to be. I'd be stunned if we get 3.6 kilowatts, because that's, you know, not how these things are rated. They're not output referred rated. So yeah, I expect somewhat less at 1 kilowatts. I don't know, because EcoFlow don't publish their efficiency curves. So I don't know, 3 maybe at 1 kilowatt. I don't know. I know that 1 kilowatt is not the same as what my fridge is going to be taking. Of course, the compressor, when it switches on, there's going to be peak currents and things like that. But, you know, like in terms of like energy, they're only briefly coming on that. As you can see, like the power was, you know, fairly constant at like 90 watts there. But anyway, yeah, it's 99%. It's like, it seems to be stuck there. It seems to be stuck on, and it's dropped right down. But there is still 400 watts, 450 watts going in there. So I'll just keep going until it tells me it's done. And it's stopped now. You can probably tell. You just hear the birds in the background, the old lab noises. Anyway, it is now 100%. So what I will do is I will now reset my energy meter here. There you go. That's just the residual power. That's microwatts, by the way. That's my 0.8 microwatts, microwatt hours, sorry. So energy meter on watt hours, okay. I'll now turn on the 1 kilowatt heater, and wait, there we go. And I can actually go back on the display here. There you go. It's actually 1.1 kilowatts, and of course, because it's a resistive load, the power factor is precisely 1, but even if we had a lower power factor, this energy meter is one of the best ones you can possibly get. So anyway, there you go. Oops, I forgot to unplug the mains input. So there you go. Now it's actually, there you go. It's 1,048, and I reset this up here, and we are at 1,068. So there's a slight discrepancy there, but that's neither here nor there. So there you go. We will, as you can see, we've got the timer there. So, but all we care about is the accumulated energy, and this thing will just switch off. Presumably when it's like 0%, it's totally exhausted, the whole thing will just switch off or drain it right down to 0. Usually not a good thing to do, but for the purposes of this experiment, we're going to build it to scale and we're going to paint it. Alright, I'm back, and according to this, we've got 1% and 1 minute left. But I was told by that person on Twitter who does apparently support for EcoFlow that it would actually stay on 1% for quite a significant amount of time. In fact, I was just at the lab and it was 4% because Mrs. EUV was reporting the figures for us, which were these. There you go. So it was a fairly linear, like every half hour I was checking it, and the progression was fairly linear like that. And now we're at 2.49 kilowatt hours, 2490 watt hours. So, you know, so from 4 to 1%, it was significant. So I don't know, I'll just wait until it actually dies. But yeah, if it was completely linear, I would have expected the 1% to have like already dropped out. So yeah, we'll see. And they can't tell, like, you know, you're measuring the voltage of the pack. Maybe it doesn't have a proper, you know, charge Coulomb counter in there, so it's probably just, you know, measuring the battery voltage and trying to, you know, guesstimate what capacity is left. So yeah, but it seemed to be relatively linear though otherwise. But yeah, there's still some capacity left. But yeah, okay, 2.5. I put this on Twitter and a few people guessed 2.5, so it's at least made that. But I don't think it's going to make 3, as I suggested that the top figure, you know, my best guess, my highest end guess would be. So someone on Twitter wanted to know the temperature. Well, like in the battery pack, and according to this, it's only 38°C, so it's not getting really hot at all, and it's blowing out, you know, yeah, I'd say that's 38 degree air. In fact, it doesn't even feel quite 38. So yeah, it's just blowing out quite cool air. But one minute, it's been sitting there for a lot more than 1 minute, let me tell you. And there's the firmware version. I did update it just like a month ago or something, so I do believe it's pretty recent, and it's still going. 2.616, so you know, we've gotten another like 100 watt hours, over 100 watt hours out of this thing at least since it went to 1%, and it's still sitting there on 1 minute and 1%. Yeah, very non-linear. Wow, still going. 2.72, 1%. Now you can avoid this sort of non-linearity problem by having what's called a proper Coulomb charge counter, i.e. you log the amount of charge that goes into the battery and then you log the amount of charge coming back out. And, you know, then you can get a pretty darn accurate indication of, you know, when the battery is dead, rather than having to just, you know, rely on the voltage and the chemistry and whatnot. So, yeah, Coulomb charge counters, you can buy specific chips to do this sort of thing, but obviously this doesn't do it, which is, you know, a bit disappointing for a high-priced, you know, real top-shelf, top-end product like this. You know, I'd expect it to be, especially when, you know, that's a lot of extra capacity. You know, many hundreds of watt hours can make a huge difference. And of course, you know, Joe average consumer, and even myself, you know, if I saw 1% and 1 minute left, I'm going to go, hey, I better, you know, unplug pretty quick, like it's going to die shortly. But it looks like I can probably, with, I think, I'm going to have to put the energy meter on the fridge and actually get you know, a proper average daily consumption, because, you know, our usage varies daily, so you've got to actually, you know, measure it over, you know, weeks or something like that to get like an average daily consumption in the current season. Of course, it's going to vary with the season, but yeah, that will give us a reliable indication then of you know, how much energy you can take out of this thing. And this chest freezer doesn't use much at all, so it looks like I might actually be able to plug that chest freezer back in, because I was getting worried when it was down near, like, you know, 5% in the morning and stuff like that. So I probably shouldn't have been. It's just quite non-linear down at the bottom end. Well, it's just hit 2.9 kilowatt hours. I could be here for a while longer. Well, there you have it. It has cracked 3 kilowatt hours. So there's a good 500 watt hours in that thing when it hits 1%. Now, the support person on Twitter, or who's done some support for EcoFlow, she did say that you can recalibrate the BMS, the battery management system in this, by discharging it or something. I don't know, I can't remember the exact details, but yeah, it's still 1% and 1 minute. So maybe after all this, when it actually dies, it will go to 0. Maybe it'll learn, perhaps. That'd be nice, but yeah, that would require another complete test. So it's done at least 3 kilowatt hours, which was my guesstimate of, sort of like my upper guesstimate of where it would do it. It's currently actually 3.03, so it's just over. Maybe it'll get to 3.1. Don't know, but surely it's got to die soon. And that's about what I expected, because the efficiency of the AC inverter in here, but, like you expect some losses in it, like 85% efficiency maybe in the inverter and the other battery, losses in the battery and all the battery system. Like, it's a complete, you have to take into account the complete system loss inside this thing. And of course the least efficient outputs are going to be the mains outputs, because the DC to DC converter outputs, they're going to be much more efficient. And I do believe it tells you this in the manual. So to get closer to the 3.6 kilowatt hour capacity of this battery, I would have to retest this, probably using, I think the most efficient one would be the 12 volt DC output on the side, the the car cigarette lighter output. That should be the most efficient output, I think. So, you could probably achieve like 95% efficiency easily with that. But in any case, you might think that we'll get more capacity out of this at a lower load than the 1 kilowatt that we're actually using here. And yes, it is actually still a kilowatt, as you can see down there. But I don't think so. I don't think it's going to make a huge difference, because this thing has, I think, got I think it's 3 kilowatts peak. So if you're not designing the efficiency of your AC inverter in here to, if it's not sort of like as efficient it can be at around about like a third of that at 1 kilowatt, then it's probably not an optimized design, I would say, anyway. So I think 1 kilowatt's a fairly good test. It's 1/3 of its maximum load. Of course, if it approaches the maximum, if you try and pull 3 kilowatts from it, you'd expect it to get the efficiency to drop, as I showed on that bathtub curve here. You would expect it to get a lot more efficient, but it should be a fairly wide, flat efficiency across here. And of course, if you draw like only a few watts from it, then it's going to be very inefficient, because then you'll get loss in the DC in the AC inverter in there. So yeah, but I think it should be relatively flat. But we'd have to do lots of parametric curves to find that out, of course. So unfortunately, that's not that easy, because you've got to repeat this entire capacity test for each different load, and then you'll get a capacity efficiency figure for each load. So yeah, it requires a lot of testing. But wow, look, I think it's going to hit probably hit 3.1, but I'm still waiting for it to die. Goodness. Now, the other thing that immediately springs to mind here is this damaging the battery? Like, just wait until it absolutely if it just cuts out and dies. Is that bad? I hope not. I hope that doesn't, damage the, over discharging the battery or whatever. But yeah, it does give me the heebie-jeebies a bit. Anyway, having, the lasting this long at 1%, 1 minute capacity, it's like, is it measuring the voltage correctly? Like the cutout, presumably there's a cutout voltage, and if it drops below that, is like, I don't know. Anyway, come on. Surely it can't get to 3.2. Oh, come on. Seriously? This is just getting ridiculous. And here I am standing here, like, in front of a heater. Oh, no, hang on. It died. There you go. It's like, it actually cut, like, it didn't, like, the display didn't physically die. It's still 1%. It still says 2 hours left, but it actually cut the AC output. I wonder if I turn that back on, will that make a difference? Anyway, capacity 3.285 kilowatt hours. There you go. Anyway, I was about to say that luckily I'm standing next to a freezer because I've got a heater going here, and I can highly recommend these New Zealand tropical juices. Good stuff. All right, so let's actually switch this back on, but maybe we'll get like another minute or something out of it, but I expect it to die again very shortly. There you go, 35 minutes, 4 minutes, 2 minutes, 1 minute. Yeah, like you can probably do this a few times, you know, to extract some energy. But yeah, it looks like it does have like a reasonably safe cutout on there anyway. So I'll just see if we can top 3.3 here, shall we? No, there we go. No, I didn't even have to edit that clip. And no, it's gone ski. So there you go. Basically, almost call it 3.29. Or no, it's the one we had before when I actually first did the cutout. So there you go. What the actual true battery capacity inside this thing is, like in terms of the actual batteries, not the output referred one, which we're measuring now. The output referred one is that 3.3 kilowatt hours at 1 kilowatt. That, as I said, that will change depending on the efficiency curve of this thing, which we do not know. So we only have one data point now at 1 kilowatts, but that's quite useful. So I really didn't need to worry about having two fridges plugged in at all, because, like, you know, I was panicking when it got below 5%. Oh, it's not going to make it, you know, whereas it had an extra, almost 800 kilowatts, 800 watt hours of extra capacity at 1%. At 1%. So maybe now it's like it's recalibrated itself, maybe. So if I repeat this test, I don't know. Let me know in the comments down below if you want me to repeat this test and or repeat it with, like, to see, like, can we actually get 3.6 kilowatts hours out of this if we use the most efficient output, which I believe would be the DC to DC converter. It wouldn't be the USBs here, I don't think. I think it would be the 12-volt output on there. But once again, it'll have its own characteristic curve, like, you know, so, geez, you could, it takes a lot of effort to characterize this, but the manufacturers should have done that. And they should publish characteristic curves, I think. I mean, you know, surely if they haven't measured it, then they'd be very surprised. So why not, you know, share the data with us? Anyway, hope you found that interesting. I certainly did. I might recharge this thing back up. The sun's still out, and then charge it for free, and then I might run the two fridge, the internal fridge and the freezer from it, so without too much concern. Anyway, yeah, I might also put the data logger here on the fridge as well, just to find out how much it does use. I've done it before, but I kind of lost the data. I think it's about like 1.5 kilowatt hours, but that was back in October last year I did that, so I don't know. It's going to vary with season and usage. Anyway, if you liked that video, please give it a big thumbs up, and as always, discuss down below. Catch you next time.